Hi, I'm Liang, and today I'll present to you our work on improving object permanence using action annotations and reasoning. This work was carried out at the Institute of High Performance Computing at A*STAR, Singapore. When robots operate in uncontrolled environments, they often lose sight of objects. This is particularly true for eye-in-hand robotic systems. They generally use a pre-trained neural network to detect objects. But detection failures can occur due to several reasons, such as noisy data, different lighting conditions, partial occlusions, etc. This is why robots need object permanence. Object permanence is a fundamental concept that describes the understanding that objects still exist even when they are not perceived anymore. Psychologists believe that children develop object permanence at the age of 2 years. In robotics, it is an important concept for belief management and perspective taking. In recent work, we proposed an action-aware perceptual anchoring model, which uses high-level reasoning with low-level object detection to improve the robot's object permanence capabilities for complex tasks. It performs an object alignment for consecutive frames and hypothesis reasoning for objects that become occluded, move out of view, and considers agent actions to infer attachment relations to track lost objects. We believe that agent actions can be used to improve object permanence because relying only on low-level perception is not enough. Take, for example, this image sequence. There are two possibilities for the oil plug. Either it is occluded and doesn't move with the hand, or it's carried, which means that it will move with the hand. So knowledge about the executed action can help us infer this hidden state. Similarly, for robots, they can use knowledge about executed actions such as pick up, insert, or screw in to infer the hidden states of objects that are no longer perceived by the object detector. So for this, we defined object attachments as a semantic relation as given an attach action AS at a time step S that causes two objects C and P to be physically bound to move together, and a detach action AT at a time step T that counteracts AS, we define an attachment relation between C and P that holds for the time steps from S to T. We refer to C as the child and P as the parent, and this is a one-to-many relation, which means that one child can only have one parent, but one parent can have multiple children. We can then generate an attachment hierarchy, which means that given a set of attach and detach actions, a list of executed actions at each time step T, we can generate an attachment hierarchy as shown in algorithm 1. We simply iterate through each action for a time step, and if it is an attach action, we add this relation into our hierarchy. If it is a detach action, then we remove it again. Take, for example, a list of executed actions where the robot first screwed in a plug into the case, then inserted the shaft into the case, and then picked up the case. This would generate the following attachment hierarchy, where the plug and the shaft are children of the case, and the case is a child of the hand. In our recent work, we compared the performance of rule-based models with a neural model called OpNet, which consists of two LSTMs. We used the allocator dataset to compare the performances on different object permanence tasks, where objects were visible, occluded, contained, or carried. As you can see, APA outperformed the other models. So in our current work, we argue that agent actions can improve object permanence in both rule-based models such as APA, but also neural models. So for this, we augmented the neural model OpNet with agent actions. So there are different ways to include the attachment hierarchy in a neural model. We can either include it as a three-dimensional feature vector, but a more efficient way is to include it as explicit guidance. So this means that we can create an object tracking vector from the attachment hierarchy. We then perform a weight augmentation and multiply the corresponding element in the object tracking matrix. And optionally, we can perform softmax on the matrix to normalize the weights. Theoretically, this augmented attention incorporates explicit guidance on the object to track, and we can vary the strength of the guidance by changing the weight parameter W. We then performed quantitative experiments on the allocator dataset, which consists of 14,000 videos. Each video consists of 10 seconds, 300 frames, and 5 to 15 objects of different shape, size, material, and color. The dataset is also annotated with 4 actions: slide, pick and place, contain, and rotate. We benchmark on a snitch localization task and use the intersection over union as well as the Euclidean distance for evaluation metrics. We compared the following models: OpNet using the same model setup and hyperparameters as provided by the authors, OpNet with explicit guidance where we experimented with different weight values and with and without softmax and chose the one that performed the best. We also performed an ablation study where we compared the performance of our perceptual anchoring model without considering action information. And finally, we compared different variants of AAPA with different object alignment thresholds. All models receive the same bounding box input, which is provided by either an object detector, which is a faster RCNN pre-trained on the allocator dataset, or perfect perception, which consists of ground truth locations of bounding boxes. We generate the attachment hierarchy using the algorithm described earlier and the given actions contained, where one object contains or covers the other object, and pick and place, where the object becomes uncovered again. Here you can see the experimental results. When we compare OpNet with OpNet AA, the performance is similar, and where OpNet still outperforms OpNet AA. This is due to the fact that in some frames the detection module does not detect the parent object containing the snitch and classified it as something else. So then the bounding box information of the parent object is 0 and the product will be 0 again. When using perfect perception, these detection errors do not occur, and the performance of OpNet AA improves significantly. Then we compare AAPA with its different variants and also without action information. We can see that without using the action information, the performance on carry tasks drops significantly. Overall, AAPA with an object alignment threshold of 6,500 performed the best. When using perfect perception, we can see that the performance of OpNet AA jumps significantly, outperforming all other models on carried tasks. For AAPA, the higher threshold performs the best because there are no object detection errors. Here you can see a comparison of the models on a carried task. AAPA without the action annotations does not track the object at all. For OpNet, we cannot explain why it did not manage to track the object due to the neural nature of the model. But for AAPA, since it is a rule-based model, it allows us to investigate failure cases. One of the failure cases is the automatic size adjustment for the predicted bounding boxes. Since AAPA maintains the last detected size of the bounding box, it does not adjust the size when it is moving in 3D. For the neural models OpNet and OpNet AA, they learn this size adjustment during training. This is why the predicted bounding box size can affect the model performance when we use the mean intersection over union. We also perform qualitative experiments in both a lab setting with a UR5 robot and a 3D printed gearbox, and an industrial setting with a UR16E robot and a real metal gearbox. The robot received bounding box information from a faster RCNN object detection, which was mounted on the robot for an eye-in-hand robotic system. We use IROS, the cognitive architecture, for for world state inference and action execution. Here you can see a demonstration in the lab setting where the robot has to pick up a plug using the eye-in-hand system. On the bottom right, you can see the faster RCNN object detection. On the top right, you can see the maintained objects by AAPA. We can see that even though the object detector fails to detect the object, our system maintains the attachment relation. Here you can see another example for inserting a subassembly into the case. The robot loses sight of the input subassembly once it has inserted it, but we will maintain the attachment relation using AAPA. Finally, here is a demonstration in a real industrial environment with a universal robot, where it has to perform a human-robot collaborative task to insert 3 subassemblies into the case. The robot maintains the case even though it is not perceived anymore. In conclusion, we proposed an approach to infer object attachment relations from agent actions, which can be used for both rule-based models such as APA and neural models such as OpNet to improve their object permanence capabilities. We compared the performance and impact of using action information on the allocator dataset, and we performed an ablation study to compare APA with and without action annotation, as well as OpNet and OpNet AA, as well as different APA variants. We have shown that action information improves object permanence for carried tasks, where APA outperforms all other models using the object detector, and OpNet AA outperforms all other models using the perfect perception. We integrated APA with the cognitive architecture IROS on both the UR5 and UR16 robot and demonstrated their use in a lab and industrial setting. For future work, we want to infer attachments from other actions such as fasten, nail, etc., and also apply attachment relations to other MOT domains, such as tracking a human who enters a vehicle. We also want to learn attach and detach actions from observation. Thank you very much.